Our last problem here in Chapter 5 really puts everything together. It puts everything from Chapter 2. We have to put names into formulas. Chapter 3, formulas into balanced chemical equations. And then we have to think about limiting reactant. Okay, and our plan actually already tells us we're given amounts of 2 reactants. Okay, this is different from the problem that we just did, problem 511. They gave us amounts of one reactant. We had to figure out how much of the other reactant we need. In this problem, as we'll see as we start writing down the pieces of information we know, they give us amounts of both reactants. So when we think about how much product we're going to form, we need to think about who's the limiting reactant. So let's break this problem down and write down information we know, including a balanced chemical equation. So alkali metals, those are in group 1A, the first column in the periodic table, react with halogens, group 7A, and they form ionic metal halides. So we'd like to know what mass of potassium chloride forms when we have 5.25 liters of chlorine gas at 0.95 atmospheres and 293 K reacting with 17 grams of potassium. So here's our chemical equation. We're going to have chlorine gas that reacts. So again, chlorine comes as a diatomic gas reacting with elemental potassium, so potassium solid, and making KCl. Potassium is going to be a +1 cation, chloride is a -1 anion, and so those combine into 1-to-1 ratio and we get KCl as an ionic solid. Because chlorine comes as a diatomic gas, we know that we have to have coefficients of 2 in front of each of these in order to balance our chemical equation. They tell us that we have 5.25 liters of chlorine gas at 0.950 atmospheres and 293 K. And we're reacting that with 17 grams of solid potassium. The question asks us, what mass, how many grams of potassium chloride can we form? So again, hopefully it's obvious to everybody to see from all the work that we did in Chapter 3 that we can use PV equals nRT to figure out the number of moles that we have of chlorine gas. We can use a molar mass to figure out the number of moles that we have of our potassium. And we can use our balanced chemical equation to figure out the number of moles of KCl that each one of these will make. Whoever makes the least is our limiting reagent. So moles of KCl, moles of KCl. Whoever makes the least is our limiting reagent. We take that limiting reagent and take that one to go on to figure out the answer to this problem using, again, the molecular weight of KCl. So what makes this problem different and applicable to Chapter 5 is we now need to use PV equals nRT to find out the number of moles of our gas. So again, lots of ways. Now we have 4 ways that we can figure out moles. If we're given mass, we can use molecular weight to give moles. If we're given a volume, we can use molarity to give moles. If we're given a number of entities, we can use Avogadro's number to get moles. And now in this chapter, we can use PV equals nRT to get moles of a gas when we know the pressure, the volume, and the temperature of that gas. So let's go ahead then and do that for chlorine. So for chlorine, to solve PV equals nRT for the number of moles, N is equal to PV over RT. So we've got 0.950 atmospheres. Notice that this problem was made quote-unquote easier by having everything given to us in the correct units. 5.25 liters. R is again our 0.08206 liter atmosphere per mole Kelvin. And that gas is at 293 Kelvin. That gives us 0.207 moles of chlorine gas. 1 mole of chlorine gas will make 2 moles of KCl, and that tells us that we can make 0.414 moles of KCl from the amount of chlorine that we have. Now remember, for limiting reactant problems, we need to essentially carry the same calculation through using our other reagent. So for solid potassium, we have 17 grams of potassium. The molar mass says 39.10 grams of potassium is 1 mole of potassium. So we have 0.435 moles of potassium. For 2 moles of potassium, we can make 2 moles of KCl. That tells us that we can make 0.435 moles of KCl from the amount of potassium that we have. This number is smaller, so this guy is our limiting reagent. So we continue this problem forward using the molecular weight of KCl, using only our limiting reagent material. So 0.414 moles of KCl. That again is our limiting reagent. We use the molar mass. 1 mole of KCl is 74.55 grams of KCl, and so the maximum amount we could make is 30.9 grams of KCl. So let me just give you a heads up of how we could tweak this problem, how I could make it a little bit more difficult. You could add on a little extra part that had something to do with theoretical yield or percent yield. I could say, give you this information and then say something like you isolated 28.7 grams of KCl. Calculate your percent yield for this process. And then again, you need to take your 27.8 grams and divide by the 30.9, multiply by 100 to get a percent. So lots of different ways that we can kind of tweak problems to make them new, and that's often what I do when I have exam questions, is I kind of take an existing problem and I tweak it. Note for this problem, if you actually happen to compare just the moles of reagent, you'd get this problem right, because if you pick the lesser number here, you'd get it right, but that would be coincidental. Note that if I had, for example, say 0.307 moles of chlorine gas, that would have given us 0.614 moles of KCl, making this guy the limiting reagent. So remember, you can't compare amounts of reactants to determine your limiting reactant. You need to convert each of those into the same product and compare those. That was the one method that we used for determining who was a limiting reagent.